This is the first question from the first question set. It's use substitution. We're given the substitution to use. Now the first thing that we'll look at are what we're integrating here. It's 1 over x squared plus 4x plus 8. Now ideally I would like to be able to factorise that, maybe some partial fractions, but on looking at it I see that I'm not able to factorise. What I'm going to do is I'm going to complete the square so that I can separate out that way. So x plus 2 all squared, I'm subtracting the 4 and adding the 8, so it's plus 4. When I do that I realise I've now got x plus 2 which appeared in the substitution I asked for. So that's nice, I'm feeling pleased about that. So now, what I'm trying to find is the integral of 1 over x plus 2 all squared plus 4 dx. And for substitution, of course, I'm looking to make sure that everything in here I can express in terms of theta in this case. The x plus 2 is no problem, that can be done. The 4 is just a 4. I need to find the dx, so I'm going to differentiate x. In order to do that I need to rearrange. So I'm currently being given that x plus 2 equals 2 tan theta. So therefore x must be 2 tan theta minus 2 dx by d theta is going to be tan theta differentiates to sec squared theta, so it's going to be 2 sec squared theta, and the 2 differentiates to 0. So dx is equal to 2 sec squared theta d theta. So now I look, I have my x plus 2 in terms of theta, my 4 is not a problem, and I have my dx in terms of theta. So I'm ready to perform the substitution and integrate. Okay, on our first substitution, remember we don't try to tidy anything up at this stage, we simply substitute in. So I've got 1 over, instead of x plus 2 squared, I've got 2 tan theta all squared plus 4. Instead of dx, I've got multiplied by 2 sec squared theta d theta. I'm going to kind of tidy up this bit under here, first of all. The 2 squared is going to give me 4, so I can see I've got a 4 common there, so I'm going to take that out. Tan squared theta plus 1. And that's multiplied by 2 sec squared theta d theta. Now, here is an identity that I need to recognise. Sec squared theta is equal to tan squared theta plus 1. What that means is that I have the same on the bottom as I have on the top, so I can divide both the bottom and the top by sec squared theta, and in the end all I'm integrating then is 2 over 4, or a half. And a half integrates to theta over 2 plus c, because it's indefinite, and I'm going to substitute the theta back in. In order to do that I need to rearrange my original substitution. So I had x plus 2 was equal to 2 tan theta. So x plus 2 over 2 is equal to tan theta and theta is the inverse tan of x plus 2 over 2. I'm going to substitute this back into here, which gives me 1/2 inverse tan x plus 2 over 2, plus c. Second question is in two parts, and both are differentiation. First one lets us do what we like, the second one specifically tells us to use logarithmic differentiation. I can see straight away with this first one I've got a product. So it's root x times e to the minus x. So u is root x, u dash is 1/2 x to the minus 1/2, or more nicely 1 over 2 root x. V is e to the minus x, v dash is e to the minus x multiplied by the derivative of this function here, which means multiplied by minus 1, so it's minus e to the minus x. What we're using here is the product rule, so I'm just going to state that. It's u dash v plus v dash u, and I'm going to substitute in. So 1 over 2 root x times e to the minus x plus, it's actually minus, so it's plus the negative, so minus e to the minus x times root x. I'm going to tidy this up. There are a couple of ways of doing that, but essentially we need to factorise. We can either choose to rationalise this denominator by multiplying by root x, or we can make a common denominator for this one of 2 root x by multiplying the top by 2 root x, and then we can subtract the fractions and pull it out, so I think we'll do that one. So we've got e to the minus x over 2 root x. There's one of them there, minus, and this one, when I convert it to 2 root x, would be multiplied by 2x. And I'll just put that at the side here. Times by 2 root x over 2 root x, which would give me e to the minus x. Root x times root x is x, so that's times 2x, all over 2 root x. And you can see that the common factor is removed, multiplied by 2x. Okay, that was part A. For part B, we're asked to use logarithmic differentiation to show that the derivative can be expressed in this form, stating the values of a and b. So we're going to start by taking logs of both sides. So ln y equals ln of all of this, x plus 1 squared times x plus 2 to the minus 4. Now, before I do any differentiation, I'm using my log rules to rearrange. These multiply together, so it's like the log add, using our log rules. So ln of x plus 1 squared plus ln of x plus 2 to the minus 4. Again, using my log rules, I'm going to move my power to the front. So that's going to give me 2 ln x plus 1 minus 4 ln x plus 2. Just keep that in there so I'm remembering what it is. Now at this point I'm going to differentiate all the way through. I have x and y so it's implicit, so on the left hand side I'm going to have 1 over y dy by dx equals, and the differentiation factor we're using here, the standard derivative, is the ln x is 1 over x. Remember, if there's a chain, you need to multiply by the derivative of what's inside. In this case, both of these have a derivative of 1, so we don't need to worry about that. So it's 2 over x plus 1 minus 4 over x plus 2. Therefore, dy by dx is equal to 2 over x plus 1 minus 4 over x plus 2, all multiplied by y. And the constants that we're asked about, a equals 2, and b equals minus 4.